webinar presented by Frank Thomas and Francois Père. Frank Thomas graduated from Ohio University with a BSEE in 1983. Frank started his career as a sales support engineer for a California-based test equipment manufacturing company. Frank has held a number of roles in sales support and technical sales prior to joining Adaptive Corporation in 2006. Frank's current role involves managing the metrology business unit at Adaptive. This group provides solutions that are used for inspection and reverse engineering. Adaptive provides services in this area and markets the hardware/software when required to solve an ongoing customer need. All attendees will be on mute during this presentation. Please enter any questions into the question box on your toolbar. This session will be recorded and added to the COE website for all members to view. Enjoy.
Okay, super. Thank you, Tori. So first of all, before we get started, I would like to thank Tori and the folks in the COE community for sponsoring this topic today. I suspect everyone on the call has had some experience in reverse engineering. Many of us have performed reverse engineering via tape measure, calipers, and manual methods. Gather dimensional information and recreate something in 2D or 3D CAD. Depending on the application and complexity, this may be a simple process or one that's more complicated. Many times you don't get all the information you need to recreate the part, and there are multiple iterations that require more time. Perhaps some of you have experienced leveraging a service bureau to scan and perform work off-site, sending you CAD data when the job is complete. This is actually a common practice, especially when you need the services only once or twice per year. Many companies are looking to expand their business by offering aftermarket products. This business requirement is driving the need to implement tools to expedite the process and deliver superior quality aftermarket products. Our agenda today introduces the process of going from scan to CAD for duplication and part reproduction. First, we will discuss the process of acquiring the image, which is the 3D data from the physical part. We will briefly introduce the tools and demonstrate 3D scanning. Next, we'll demonstrate the process of cleaning the scan data and getting it into a usable CAD format. This is a process many people are not familiar with, so we will review the roadmap at a high level to expand your appreciation of what is involved. My name is Frank Thomas. As Tori said, I'm a metrology solution specialist within Adaptive. I'm joined today by Francois Père of Creaform. Francois is a reverse engineering expert with the Creaform organization. Francois will offer a technical demonstration of reverse engineering, specifically in CATIA V5. Many of you on the call today are familiar with Creaform as a Dassault Systems partner years ago. What you may not know is that Creaform also manufactures a wide portfolio of metrology hardware for inspection and reverse engineering. The metrology solutions team here at Adaptive specializes in delivering these solutions as well as offering contract services to clients who only have occasional needs. Now a couple of words about Adaptive. Adaptive is a Dassault Systems value-added reseller. Over the years, we've expanded our focus from product development, leveraging the Dassault Systems portfolio of products, into now the quality part of the manufacturing process. Much of our expansion today is in the area of QA and QC, in inspection, in PPAP and AS9102, as well as reverse engineering. Adaptive has been a proud member of COE since our inception in 2007. We value our relationship with the COE community, and we are here to educate and serve. Our clients span many industries ranging from automotive to aerospace, including consumer products. So we have a couple of polls today. Tori, if you've got the polls active, if we can activate the first poll. Thank you. So the first poll, just to kind of engage some folks and get some feedback so that we understand our audience a little bit better. If you would, please select one of the following. What is your interest in reverse engineering? Is it for aftermarket expansion? Is it for documenting legacy products? Is it to capture the customer envelope of requirements? So maybe you're going to replace a part on a machine that you built 30 years ago, and you've got no CAD, you've got no 2D drawings, and I need to go out and scan the area so that we can duplicate that part. Or maybe it's all of the above, some combination of all of the above. So we'll take maybe 30 seconds if you would select one of these options here. And then we'll share the results with the audience here so that we get a feel for what the cross-section of the group looks like. Tori, I'll defer to you.
Yeah, it looks like we are at 5% after market expansion, 34% are document legacy products, 7% capture customer envelope requirements, and 54% are at all of the above.
Okay, wonderful, thank you. So it's really a pretty mixed group, so that's good. And I think that you'll all find the topic today of interest, which leads me to the next poll. So Tori, if you would show poll number 2. By the way, just to keep things interesting, we're only doing 2 of these. So the next question is, how frequently do you have an application for reverse engineering? Is this something that, gosh, it comes up pretty frequently, maybe monthly, maybe quarterly, maybe yearly, maybe almost never? So if you would select one of those options, and again, give us some feedback. I suspect that in most organizations, this is probably something that comes up on a fairly regular basis in one way or another. But, you know, we appreciate your feedback. Tori, I'll defer to you.
Okay, we are at 36% frequently, 8% monthly, 31% quarterly, 21% yearly, and 5% almost never.
Oh, gosh. Okay, so again, a pretty good cross-section. So for those of you that, again, are addressing this fairly frequently, I think that you'll find the webinar today very relevant. So moving on, let's talk a little bit about the various types of 3D scanners in the market today. There are different kinds of 3D scanners on the market today. One type of scanner is generically referred to as the laser tracker. And the laser trackers are high accuracy measurement devices that are great for large, high precision products. So again, the key there being large, and the second key being very high precision. Laser trackers actually almost hold the tolerances in many times of CMMs. The next type of scanner is on a portable arm, and the typical size of arms range from 6 to 8 feet. Typically, arms on the end of the arm will have a probing head as well as maybe a scanning head. The issue typically with arms is really just kind of being able to manipulate it in the environment that you're trying to scan. Many CMMs can be retrofit with 3D scanners, but they tend to be slow and rigid and require clean room environments to function. Photogrammetry involves the use of cameras and software to stitch together images or pictures of the object into a 3D image. Handheld scanners are growing in popularity due to the portability and speed. We'll show a brief demonstration of a 3D scanner from Creaform here shortly. 3D scanners are rated by accuracy. Accuracy correlates to the tolerances you are required to hold. There are many uses of 3D scanning. The two primary are reverse engineering and inspection. Today, we're going to focus on reverse engineering. In the context of reverse engineering, there are a number of areas people focus on. The largest is aftermarket business. Many companies are looking to grow their business and drive top-line revenue by introducing new aftermarket products. 3D scanning and reverse engineering are key elements of this process. Portability is a key consideration. Many times it's great to send a tech or an engineer into the field with a 3D scanner to capture all of the information required to reverse engineer a product based on something physical that only exists in the field. So we'll show you a quick 3D scanning demonstration. I'll pause here for a second. And we'll pop out to here. And you should see my screen. So here's what this 3D scanning process kind of looks like. Typically, and this is an example of a portable handheld 3D scanner gives me the ability to plug into a simple laptop. I have my physical part. As I'm scanning the physical part, literally in real time, I'm imaging the part in 3D on the computer. The software that is native to the 3D scanner, and we'll be talking about that a bit more, is used to capture the image that's coming from the 3D scanner, and this is one of the steps in the process of reverse engineering. Pause here. Okay, so now talk for a moment about where 3D scanning can be used. 3D scanning can be used really at many levels of the process, from concept through service. Companies have an application for reverse engineering in all of these areas of their business. So let's explain the process briefly for reverse engineering prior to Francois giving us the demonstration. So this will kind of preface some understanding maybe a little bit better. There are 3 steps in the reverse engineering process. Step 1 involves acquiring the image, which is the 3D scanning that we reviewed a moment ago. Step 2 is typically some process or some amount of mesh improvement to take the 3D scanned image and do some cleanup or some repair on the mesh itself. Francois will touch on that here briefly in a little bit as well. And then step 3 is to create simple CAD entities on a 3D scan that will be exported via IGES or STEP to CAD. This step is typically performed using the software bundled with the 3D scanner. Another way to look at the process is this. We scan, which results in a 3D mesh. We align our origin in the mesh, much like we do in CAD. Then we review the mesh to improve or enhance specific areas of the mesh if necessary. Once we have the mesh refined, we then can follow one of 2 paths. We can start the reverse engineering process, or we can simply take the mesh and output to a 3D printer. The mesh file is a .stl format that can be used by virtually all 3D printers. Scan to CAD, which is our focus today with CATIA, involves creating entities and cross-sections that are output in common CAD formats. Scan to 3D print does not require this step, since 3D printing does not require mathematical CAD elements. Here are some examples of data collected by a 3D scanner. You can see the quality of the 3D scan information is really quite good. Metrology grade scanners typically hold a tolerance of better than 3 thou. Mesh improvement is typically performed using the software that is bundled with the 3D scanner. This software allows the user to manipulate the scan data, which is also called the mesh, by the way, to enhance the quality of the mesh or change the mesh resolution as necessary. Some mesh improvement software will allow you to fill holes in the mesh, much like an engineer will review and repair IGES files after they have been imported to CAD. More advanced software packages offer a way of creating CAD elements on the 3D scan data and exporting those elements directly to CAD via IGES or STEP. Others can create NURB surfaces on the 3D scan data that can be exported via IGES into CAD. This NURB surface data can be used as a roadmap in CAD when recreating a part. So here we're showing properties of a scanned part prior to 3D printing in the native 3D scanning software. So I have the ability to basically scan the part, select the part, show the properties. That way, before trying to print it, I can scale the part up, I can scale the part down, I can tell how large the part is to make sure that it fits inside of my 3D printing envelope. Here we're showing the ability to auto-surface a scanned part in the native 3D scanning software. These surfaces can be output to CAD via IGES, as I mentioned earlier. There are a variety of advanced software options to post-process the 3D scan data. Here's a list of the more common products. Most packages, including CATIA v5, require add-on or upgraded versions of the package to import 3D scan data. The format output by most 3D scanners is a .stl file. This is the same format, as I mentioned earlier, as required by 3D printers. So now let's get into CATIA v5. Let's get into reverse engineering specifically in CATIA v5. In the case of CATIA v5, to import the .stl file, you will need an add-on package for PLM Express that is called REE. REE includes the following workbenches. The first workbench is called QSR, which stands for the Quick Surface Reconstruction, which allows you to select points on the .stl file and create surfaces quickly. DSE is also part of this workbench, which allows you to manipulate points. GS1 is for shape editing and design. DSS is for advanced shape design. And TL1 is used to import the STL format file from the 3D scanner. So in other words, if you are looking to do reverse engineering in CATIA v5 PLM Express, you will require this REE add-on workbench for CATIA. So with that, I'm going to pause here for a moment. We'll turn over the presentation to Francois for the demonstration of reverse engineering in CATIA. Francois, over to you.
All right, thank you, Frank. Well, hi everyone. So as Frank already said, my name is François Paré, and I am working for Creaform as a metrology expert, and I've been doing that for the past 5 years. Prior to that, I was also a CAD instructor, well, also for Creaform. So today I will describe briefly an example of the reverse engineering process and workflow to go from the scan data to a CAD model using CATIA. So the next video has been fast forward 3 times. So in fact, it took me half an hour to complete this process. So in order for you guys not to stand in front of your computer too long, it lasts only about 10 minutes. All right. So all right, Frank. So you can go on with the video. So here I'm going to first start by importing my mesh file. So like Frank said, it's a .stl file, and it's a symmetrical file, and it's a good practice to actually copy this original mesh, as all of the other operation you'll do on it cannot be undone. So if you delete something, or which I'm going to do like that. Now, as the part is symmetrical, I can actually keep only a quarter of my mesh and base my design on it, so I'll be then able to create mirror to get my final CAD model. So here we'll create the first sketch, or the first outline. I like to create different bodies and then just merge them or subtract one to other at the end using Boolean operation. When you create your first sketch, well, there's many different ways you can create sketches. Here I'm going to use the more simple way. So I basically simply create profiles and creating them visually over my mesh boundaries. As I'm doing so, I can edit the dimensions so I can get a full parametric model, and of course create different constraints, like if you were designing a brand new part. Okay. There's, as I said, there's more ways of creating sketches and more accurate ways of doing so. One of them is to create anchor points on the mesh, or to create a sketch from cross-sections. Cross-section that can be created in a third-party software or straight from within CATIA. For more complex surfaces, there are also the Power Fit tool in the QSR workbench. This tool creates a NURBS patch from selected mesh area. In this demonstration, I will simply use basic tools that you can find in Part Design Workbench. So this is why I'm going to create basic sketches like you can see right now, and create basic features such as extrudes, pads, shafts, and all that. So you can see my sketch is already done right now. So the first profile, you can take a look at the overview of it. Now for the second sketch, I'm going to create a more basic profile just to then create a combine. So the combine tool in CATIA creates two extrusions and keep only the intersection of both. So you can see here, very basic profile. Once again, profile based on, well, visually based on my mesh. So you can see the combine tool right now, and already we have a good definition of our part. At the bottom of this part of this model here, you can see a small cylindrical protrusion. So I'm going to create a circle here and just add some height to our part right there. Now, to remove the inside of that model, I'm going to create, again, very basic profile, visually based on my mesh, and I'm going to create a pocket to remove material from the inside of our CAD part. Okay, so this is my first body. I'm going to add a basic small hole there. You could have used the hole function, or here I'm using a pocket, so that's your choice. And at the top, you see here, we do have a revolve feature, okay, on the mesh, on our brown scan data. So this is why I'm going to create now a new profile. This time, this profile will be based, as I said, on a cross-section that you can see in light blue. Okay. So again, you could have created points on this cross-sections in order to create more accurate profiles. Here, the design is pretty simple, so I can simply put my lines and arcs and different elements of my sketch, just dragging them like that over my light blue cross-section extracted from our mesh. I'm going to add more features here. So here an arc, trim them to get a continuous profile. There it is. Few details here, really quick. And then I create my shaft feature over the same quarter of the part we have. So now we have two bodies, and we're going to keep that for more operation at the end. So of course we have too much matter here. So what I'm going to do now is to create a pocket, but this time from the top surface. So from the top view, I'm going to create once again, very basic profiles. And all these profiles are, as I previously said, editable. So you can change them, constrain them the way you want, set all the values you want, as if you were designing from a 2D drawing. Now what I'm doing is to constrain my profiles from my sketch to existing edges of my CAD model. So then I create a small pocket there to get a few details on the inside of the model. We can add these different bodies to one another. So that merge all these separate bodies into one CAD model now. At the top, we can see another protrusion there. So I'm going to create another sketch once more in order to just add some material to our CAD model. Trimming my profiles, getting a nice sketch there. Here it is. Adjust the height, and that's it. Now for the inside of the part, we need to remove some material. So I'm going to create once more another sketch to be used for a shaft, but this time to remove material. Right? So I'm going to still use my cross-section that has been previously done, but this time the inner profile to create my sketch. Again, you can see the cross-section in light blue in opposition to my sketch, which is now getting all green. Almost done now. A few details, corners and edges. And here it is, closing my profile, my axis, then revolving it. We can see the feature, and then we're going to subtract this feature there. Okay, so basically, you can see now in brown all our scan data. And even though you are missing some data, it doesn't matter in the reverse engineering process, as you just need enough information from the scan data in order to create your part. So here, from going from the biggest features to the smallest, we can add these small holes, as you just saw, at the top of the part by another pocket or with the hole feature. And on the side here, I'm going to just add a small pocket to remove this corner right there. As I said, our part is symmetrical, so now I just perform a mirror on the other side, here like you saw quickly again. And at last, we can create all our fillets all over our design. So for this part, it's going to take some time. You can also hide our CAD model, take a look at the mesh, do some modification. You can also go back to existing parametric features. So if something is not what you were expecting, well, you can go back to these features and change their dimensions, their profiles, or anything about it, as a matter of fact. So we can inspect our design visually, like you can see right now on this video, or you can also use a tool called Deviation Analyzer, which can find defects in the design, and of course you can go back and change these features as I previously said. So you see here there's a small defect there that I need to be modified with some fillets. All right, then we have our first half. We're going to mirror this first half on the other side, and we get our final CAD model. So parametric CAD model that can be re-edited as you wish. Okay, so we can take a look how well it's overlapping our scan data in brown right now. All right, that was it. Very quickly shown, but I think that show you very well a brief overview of how you can reverse engineer a part using CATIA from our scan data. So Frank, back to you.
Okay, very good, Francois. Thank you. That was very well done. Okay, so moving on and moving to wrap up. The REE add-on for CATIA offers a very powerful set of tools, as Francois demonstrated. REE enables the user to recreate 3D CAD quickly and accurately, referencing the 3D scan data. Most importantly, now I have a true CAD part that can be fully documented, parameterized for reuse, and machining using traditional manufacturing methods. If you'd like to learn more about REE, please contact your local Dassault Systems representative or reseller for more information, pricing, or information on REE. So with that, we'll move to any questions, Q&A that have been getting queued up by the audience. Tori, over to you.
Yeah, if anyone has any questions, please enter them into the question box on your toolbar, and we'll be able to send them over to Frank. Frank, do you have anything coming in on your side?
I've got 3 of them queued up here now, so maybe while you're waiting on your end, I'll go through the couple that I see here. Okay. I think Francois touched on this a little bit, so maybe Francois, to highlight for the audience, how can we analyze, this is from Mark, how can we analyze our final CAD model to know if it matches the scan data, and can we analyze the deviation between them both? Francois, over to you.
Yes, actually you can. So yeah, like I said very quickly, there's a tool in CATIA which allow you, it's called the deviation analyzer, if I'm not mistaken, between the French and English version. So yeah, that tool allows you to actually compare your CAD to the scan. So you'll know if there is any deviation, if there are, well, of course, it might have some, but if those deviations like are outside your tolerance. So you can then go back to your design and modify it. If you use parametric features like I did, so just like pads and simple part design features, you can just re-edit them, change the profiles, change the features, length or angle, whatever. And but if you use freestyle design, then you'll need to modify, like delete some of the surfaces you've created to recreate new surfaces there.
Okay, very good. Thanks, Francois. Getting some other questions here from Michelle. Please offer some information on cleaning bad cloud. So I think what Michelle is looking for, Francois, is maybe some information on how do we edit scan data.
All right. Well, in the DSE Workbench, there's few tools you can use, such as Mesh Cleaner, Decimate, Fill Hole, or you can optimize the mesh or align the mesh in a 3D space, and that will allow you to basically clean up the mesh before moving on to the reverse engineering process. Now, that said, if you import a point cloud, you'll have to mesh this point cloud first. So if you have many different sessions, you can then merge these different point clouds all together, and that'll be ideal if all these point clouds are actually in the same XYZ referential, right? So now that you've merged them all together, you can create that mesh and then clean up that mesh and then move on to features creation like you just saw.
Okay, thank you, Francois. Bob is asking, is REE only available with CATIA V5 PLM Express, or can it be ordered as an individual product? So I'll offer an answer there, Bob. The answer is it is a bundle. REE is a bundle in V5 PLM Express. In traditional CATIA, we can order those individual components separately. So if all you need is the ability to import STL, or if all you need is QSR, you can order those items individually. Corey is asking, how did you get the scan to import at the absolute origin in CATIA? Francois?
From our solution, using our scanner, there are some alignment tools that are available to the users from our own software called VX Model. So basically, you can do the alignment there, and that's how we got the mesh file to be already aligned with the absolute origin XYZ. So basically, we've created features such as cylinders and symmetry planes and all stuff like that, and then we align correctly the mesh to this referential. Otherwise, there is other tools that are available in CATIA also to do that, to do the alignment.
Okay, very good. Thank you. Next question is, what is the typical file size for an STL file of a part the size of what was demonstrated? The question is kind of around portability. How big are these files? Francois?
For the mesh file, it's not that heavy. It can be like, well, it depends on a bunch of factors, but for the file you saw, it can be from around like 3 to 10 megs. All right, so if you have, of course, a larger part, you might get bigger files, and of course, it also depends on the level of details you want your mesh file to have. So if you scan with and your final output has a lot of really small triangles, which are part of the mesh, then of course the file size can be much greater. But there is, again, in both CATIA and in our own software from Creaform, there is a decimate tool which can very easily and it can be just like reducing the file size by creating bigger triangles over flatter surfaces, while keeping very high details over detailed areas.
Okay, very good. Thank you, Francois. Next question comes from Michelle again. From the scanner that they use, they don't get point clouds or scan data that's not so clean. So maybe to offer a comment there, Michelle, many of the newer scanners bundle 3D scanning editing software that's really, really very powerful. And so we typically use the bundled 3D scanning software to post-process or pre-process the scan data before bringing it into CATIA. And that's one of the capabilities that I know Creaform has touted for years, is that their software that gets bundled with their scanners, they kind of draw the analogy of an iPhone. The iPhone is part hardware. It's also part the operating system for the iPhone that gives it the experience. Very similar kind of thing in scanning. So it could be that your scanner is, maybe you didn't acquire that software when you bought the scanner. Maybe it was an option for whatever scanner you have. Or maybe it's a little bit dated of a unit that doesn't have the fidelity or doesn't have current software. I don't know. Let's move on to Johnny offered a comment that regarding the last question, DMU space analysis product compare works pretty well to compare two parts as well. Fabi has a really good question here, so I'll pose this to you, Francois. Is there a way to import the scanned mesh directly into a part or drawing without the need to model it as it was done in the illustration? Francois?
Not that I know of. You can import an STL file in many different softwares, but they will basically be only an image, so you won't be able to pick points on them or use them to create profiles if you don't have this add-on package like we said about CATIA with the REE. So you could probably get a drawing about just an image to do basic views or snapshots, but not extracting dimensions or lengths or distances or clean profiles. Well, not that I know of.
Okay, very good. Ted has a good question here. The steps shown in the demo to recreate a parametric model from the STL are still fairly manual. So Ted is asking the question, is Dassault working on some future capabilities to improve? Ted, I'll take kind of a stab at that, maybe then defer to Francois to offer his input. What I can tell you is that our friends at Dassault Systems see the ability to handle 3D scan data in all of their products is very, very critical. It's very important to our customers, and they are investing heavily and focusing heavily on this area to enhance the ability to work with 3D CAD data for reverse engineering and in other parts of their portfolio in the area of inspection as well. Francois, over to you. Any comments?
Well, yeah, like I said during the demonstration, using the PowerFit tool in the QSR Workbench works pretty well to create a complex surface, and that you can create many different complex surfaces and just blend them or trim them all together at the end to get your complete CAD model. So even though if in the video we saw only basic features such as pad, shaft, and everything, there's all the tools you need in CATIA in order to do very complex design. Yeah, that's it.
Okay. All right, Tori, I see a couple other questions. Do we have time for at least one more question?
Yeah, we have time. We have at least 20 minutes, so you're good.
Okay. So a question from Brad. Brad is asking, how can we apply this to creating surfaces from a scan where solid modeling isn't an option? So I guess, can we just do surface modeling because either solid modeling isn't an option, or maybe what Brad is asking, maybe I don't need a solid, I just need a surface model. Francois?
Yeah, you can definitely create only a surface model. Like I said, with the QSR tools and like your freestyle tools that you have in your freestyle workbench, you can just create those power-fitted surfaces and then use them as regular 3D surfaces, or you can create like 3D curves from the mesh and then use them to create your sweep or your um, loft or any tool you have to create surfaces in CATIA, just that instead of creating your 3D curves or 2D sketches or 2D curve from coordinates or 2D drawing, you will create them from the mesh.
Okay, thank you. Last question that I see, and keep in mind if you've got any other questions, we've got a few minutes here. We'll try and answer as many as we can. But last one that I see here on the prompter is from Zach. Zach is asking, can you demonstrate the CATIA tools for aligning and orienting the mesh? I'll defer that to Francois, but before I do, I think that that can be done at a couple of levels, I believe, and Francois will offer some detail. Maybe I could do that at the mesh improvement level, or in the creating the origin before I output the mesh, or it can be done at the CATIA level. I assume either place, but Francois, over to you.
Yeah, so according to the device you're using, there are some devices that offers these alignment tools, and for that you'll need to extract entities such as planes and cylinders and all that, and then use these entities to pair them up with the basic axis, so XYZ basically. So in this example, we use some planes, then averaging these planes, so get the central plane to get the origin to be dead in the center of that part. And I think that we use also the axis of the bottom holes in order to get the origin to be, or is it the top hole? I don't remember. But yeah, so according to the part you have and the device you're using and the software you bought, you should also get these alignment tools either in your device software, or you can use the same kind of process in CATIA using extracted entities from the scan data.
Okay, very good. Thank you, Francois. So with that, we'll go ahead and wrap up. Tori asked us to offer a simple reminder. Co-membership renewals can be performed on-site via this URL, and I'm sure that Tori's going to be publishing the details of that after we wrap up the webinar today. Also, the co-national event is in San Antonio, Texas this coming year, and the dates are April 10th through 13th. Registration and more information is available via this URL as well. So Tori, with that, over to you.
Great. Well, thank you everyone for attending today's webinar. Thank you, Frank and Francois, for presenting. If you come up with any further questions, please feel free to email co@co.org and we'll get them over to Frank and Francois. And you can look for this presentation to be published on the Co Ask the Experts archive online. Thank you.
Thank you. Bye.
All right, thank you.